Yeah, screen is visible. Screen is visible.
Yes, sir.
Okay. Now, nonlinear programming. Nonlinear programming. Problem. See, already you know the linear programming problem. Okay, in LPP, just we called it as in LPP. What is the objective function and the constraints are both are linear. For example, if I consider one maximization problem, maximization z equal to 8x1 plus some 2x2, subject to the constraints x1 minus x2 may be greater than or equal to or something less than or equal to x2 less than or equal to 3, and non-negative restrictions are there greater than or equal to 0. Okay, in this LPP, what we have, see, the variables are x1, x2. Variables are x1, x2. Those are at degree 1 only. Those are at degree 1 only. That is called linear. And the variables do not multiply together. Variables do not multiply together. So, I am giving one expression. I am giving one short definition for non-linear. What is meant by non-linear? What is meant by non-linear? Non-linear means in any expression, if all the variables, let me tell you first linear, then I will go for non-linear. All the variables occur at degree 1, and they do not multiply together, then that expression is called linear expression. See, once again, what is the thing here? All the variables occur at degree 1 only, exactly like this, and they do not multiply together, x1 into x2, x2 into x3, not like that. Then that expression is called linear. Otherwise, it is called non-linear. Otherwise means what? If any one variable is occur at degree more than 1, occur at degree more than 1, otherwise it is called non-linear. The variables, at least one of the variable degree is more than 1, and the variables are multiplied together, then that is called non-linear. Now, what is the general form? And in non-linear programming problem, simply I will write non-linear programming problem as NLPP. What is this? In NLPP means a brief definition. This is called objective function. And these are called constraints or conditions. Either the objective function or at least one of the constraint is non-linear. Or both, means objective function as well as constraints or non-linear. Non-linear means what? The variables occur at more than 1 degree or they multiply together. That is meant by non-linearity. Okay, either the objective function or the constraints are non-linear, then it is called non-linear programming problem. So, what is the general form of the non-linear programming problem? See, general form of NLPP. What is that? The objective function is either maximum or minimum, so called optimize. I will write like this: let z be a real valued function. Z be a real valued function of n variables, real value function of n variables, so say x1, x2, xn, x1, x2, xn. That is, z is a function of n variables defined by z equal to f of function of x1, x2, and so on xn. Function of x1, x2, so on xn. Then I will write this optimize. Optimize means what? Maximize or minimize. Optimize z equal to f of x1, x2, xn subject to constraints. Subject to constraints. The constraints I'm taking as g1, first constraint, g1 of x1, x2, xn. It is a function. G1 means it is a function. The constraint may be greater than or equal to, or less than or equal to, or maybe equal to some right side value b1. Another constraint I will take z2 of x1, x2, xn. This is another constraint. This is also maybe greater than or equal to, or less than or equal to, or equal to some b2, equal to b2. Okay, and so on. Let me consider m constraints, m constraints, x1, x2, and so on xn may be greater than or equal to, or less than or equal to, or equal to bm, and all the variables xj greater than or equal to 0 for all j equals to 1 to n. Means what? x1, x2, xn all are greater than or equal to 0. Non-negative restrictions. Okay, you know, this is called objective function. This is called objective function. Okay, and these are called constraints. These are called constraints. Why I'm telling again? Because I need this terminology in Kuhn-Tucker conditions. And these are called non-negative restrictions. Non-negative restrictions or constraints. Non-negative restrictions or constraints. Okay, now the definition of nonlinear programming problem. The above problem is said to be NLPP, is said to be nonlinear programming problem if either the objective function f of x1, x2, xn or the constraints at least you write like this, or at least one of the constraints, or at least one of the constraints is non-linear. You know what is the meaning of non-linear now? Is non-linear, or both the objective function and constraints. Both the objective function and the constraints are non-linear. Okay, then this problem, this entire problem, optimize z equal to f subject to m constraints with a non-negative restrictions, is called non-linear or constraint non-linear programming problem. Is called non-linear programming problem. Okay. Now see, objective function is nonlinear, or constraints are nonlinear, or both are nonlinear, then this entire problem is called nonlinear programming problem, and it is general form of nonlinear programming problem. And see, what are the constraints type? Maybe greater than or equal to constraints, or less than or equal to constraints, or equal to type, Now coming to how to solve this non-linear programming problem. To solve linear programming problem, we have so many methods: simplex method, divised simplex method, two-phase method. Many methods are there. Big M method. Okay. Now, how to solve non-linear programming problem? Because of non-linearity, the simplex method fails here. Then how to apply? I think if you remember in your first semester, maximum minima function of several variables, maxima and minima of function of several variables. You learn how to find maxima and minima function of two variables, right? What is maxima function of two variables? Find the necessary conditions: dou f by dou x equal 0, dou f by dou y equal to 0. Okay, then find the stationary point, then find rt minus s square. I think you may be remembered this one in first semester, maxima minima. Afterwards, maxima minima of function of several variables is there. Maxima minima of function of several variables. What is the title there? Lagrange's multipliers method. Do you remember? Anybody? Anyone? Lagrange's multipliers method. Yes? Yes? Hello? Okay. Now, here there are cases are there. Case 1. First case. How to solve? Is my voice is audible? Screen is visible?
Yes, sir.
Right. Now tell me Lagrange's multiplier method. Do you remember?
No, sir.
No. Okay. Let me tell you again. Now, case 1 is constrained optimization. Optimization means finding maxima or minima with equality constraint. With equality constraint. See, the conditions are here, equality constraints. Constrained optimization means constraints are there, and what are the type of constraints? Equality constraints. Equality constraints. So here, say the case 1 is for equality constraint, how to solve nonlinear programming problem with a equality constraints. Nonlinear programming problem with equality constraints. The method is named as Lagrange's multipliers method. Simply called Lagrange's method. Lagrange's multipliers method. Okay. Now here consider the NLPP. Consider the NLPP. Maximize or minimize z equal to f of x1 x2. Z equal to f of x1 x2. Okay. Then let me consider if I take equality constraint with many variables. Equality constraint with many variables. Yeah, take like this: x1 x2 xn, x1 x2 xn. Let me consider with one constraint. Okay, Lagrange's multipliers method. Let me explain. Subject to the constraints. Subject to the constraints g of x1 comma x2. Let me explain the problem with the two variables. That is very easy. Then you can understand we can extend this. G of x1 x2 equal to some constant. I'm taking that constant as c, and the non-negative variables x1 x2 greater than or equal 0. See what type of constraint? Case 1, equality constraint. That is why I have considered equal to c, equality constraint. Equality constraint. And this is non-linear means what? Either the objective function is non-linear or the constraint is non-linear. Constraint is non-linear. Then here let h of x1 x2 equal to g of x1 x2 minus c. In the constraint part, this g of x1 x2 equal to c is there. Now take c this side and assume this entire g of x1 x2 minus c as h. Then what is NLPP can be written as? Then NLPP becomes, what is that? I can write optimize, maximize, minimize. I can write optimize z equal to f of x1 x2 subject to what is the constraint becomes h x1 x2 equal to 0. This minus c. C comes to here, so equal to 0, and x1 x2 greater than or equal to 0. X1 x2 greater than or equal to 0. Now define what is Lagrange's method. Define the Lagrange's function. Define the Lagrange's function as L. How many L of? Write the variables x1, x2. And how many constraints are here? I am considering only one constraint. I am considering only one constraint. Then you put one Lagrange's multiplier. One Lagrange's multiplier. And how to define Lagrange's function? First, write the objective function f of x1, x2 minus lambda into the given constraint h of x1, x2. This is Lagrange's function. This is Lagrange's function. Okay, got it? Then, as in first semester, we know that the necessary conditions for optimum means maximum or minimum. For optimum are, what are the conditions? First order partial derivatives must be equal to 0 with respect to variables, unknown variables, dou L by dou 2 x2 0, and dou L by another unknown is what? Lambda. Here what is lambda is called? This lambda is called Lagrange's multiplier. Lambda is called Lagrange's multiplier. Since only one constraint is there, we have only one multiplier. Lambda is called Lagrange's multiplier. Now, these are the necessary conditions. Dou L by dou x1 equal 0, dou L by dou x2 equal to 0, dou L by dou lambda equal to 0. Done. Solve these three equations. How many equations? 1, 2, 3. Solve these three equations. Solve these three equations for the three unknowns. How many unknowns? Three unknowns are there. What are the unknowns? Three unknowns, x1, x2 and lambda. X1, x2 and lambda. Okay, then after getting the point, therefore the stationary point is what? Therefore the stationary point is what? Let me consider this capital X equal to x1 comma x2 is the stationary point. X1 comma x2 is the stationary point. Then now whether this point gives maximum value or minimum value, whether this point gives maximum value or minimum value, I have to decide that. Okay, we have to find that. Now is the point x equal to x1 comma x2 gives maximum or minimum to the objective function? Maximum or minimum to the objective function? Let us check. That is the question. Okay, this is my solution point. This is my solution point. Now I have to check whether this point is giving maximum or minimum. Then the sufficient conditions. That means I have to decide. You write this one. Do you know Hessian matrix? Hessian matrix. Okay. The sufficient conditions. The sufficient conditions for a maximum. The sufficient conditions for a maximum or minimum require the evaluation of at each point, at each stationary point, evaluation of at each stationary point of n minus 1. This is important. Okay, n minus 1 principal minors. N minus 1 principal minors. You know what is meant by principal minors? In intermediate also it is there. Principal minor means determinant. Principal minors of the determinant. Principal minors of the determinant given below. Now we have to evaluate the following determinant. This is delta n plus 1, determinant of n plus 1 by n plus 1 matrix. This is 0. First element is 0. All of you listen carefully this one. At the stationary point x1, x2, we got the stationary point by solving these three equations. Now that point gives maxima or minima. To decide that, we have to evaluate this determinant. What is the first row? For the constraint h is there now, only one constraint we have considered. For that constraint, you find the partial derivatives with respect to the variables. 0 dou h1 by dou x1, dou h1 dou h by dou x2, right? And same thing you write in the first column also, dou h by dou x1, dou h by dou x2. Done. Over. Next one, this one, for the Lagrange's function, you find the second derivative with respect to x1, and this position, dou square L by dou x1 dou x2, Next one, dou square L by, this is 2 1 position, x2 x1, and this is dou square L by dou x2 square. We have to find this determinant. This is delta 3. You write delta 3. This 3 by 3 determinant. Okay. And that stationary point, instead of this one, you can find in another way also. What is the simple one? If single constraint is there, just you find a Hessian matrix technique. That's better. It's always better. Hessian matrix technique. Let me tell you that also. After finding this, if this delta 3 greater than 0, this positive, or you write like this. I will tell one concept of Hessian. See, Hessian matrix. All of you, this is also important to decide maxima and minima. In Hessian matrix, for your function f of x1 comma x2, the Hessian matrix is h of x. I will denote. This is always second order partial derivative matrix, dou square f by dou x1 square, 1 1 position, dou square f by dou x1 x2 1 2 position, dou square f by 2 1 position, x2 x1, and dou square f by dou x2 square, 2 2 position. Okay, this is Hessian matrix. Okay, and if h of x, just give me a minute. If h of x, that is all the second order partial derivatives matrix, write term by term. If it is positive definite, if h of x is positive definite, then f of x1 comma x2 is convex function. Then f of x1 x2 has minimum value. And coming to positive definite, what is meant by positive definite? I will write in if all the principal minors, just give me a minute. If delta 1 in this Hessian matrix, if in h of x, delta 1 means first principal minor. Means determinant of dou square f by dou x1 square. This is determinant, not mod. Remember, is positive. delta 2. Delta 2 means just this one. Delta 2 is also positive. If in h of x, first principal minor and second principal minor. Second principal minor means this one. Dou square f by dou x1 square, dou square f by dou x1 x2, dou square f by dou x2 x1, and dou square f by dou x2 square. If this is also positive, then h of x is positive definite. H of x is positive definite. When this is positive definite, what is the function is convex function. Do you know convex function? Anyone? Convex function, concave function. Convex function means the shape is like this. The shape will be like this. Function shape will be like this. Then this is then it has definitely minimum value. That's why I have quoted minimum. When f of x is convex function, then it has minimum value. Okay, this is about positive definite. Another one is if h of x is negative definite. If h of x is negative definite, then the function f of x1 x2 is concave function. Concave function. This is convex function. This is convex function. The concave function, then f of x1 x2 has maximum value. F of x1 x2 has maximum value. What is the shape of the concave function? It will be like this. So this will be the maximum value. This will be the maximum value. This is concave function, the shape of the concave function. So whenever function is concave, it has maximum value. Whenever function is convex function, then it has minimum value. Remember this point. And what when positive definite means what? The determinant of the first one by 1, dou square f by dou x1 square is greater than 0, and the determinant of 2 by 2 greater than, all are positive. All the principal minors are positive, then it is called positive definite. Now coming to negative definite. Negative definite, h of x is called negative definite if in h of x delta 1 is negative, delta 2 is positive, and so on. That is alternately negative and positive, alternately negative and positive, principal minus. Then h of x is called negative definite. H of x is called negative definite. This is the process of one constraint, one equality constraint. Once again, I'm telling you, now this is the problem. Okay, this is the nonlinear problem with only one equality constraint is there. Then how to apply Lagrange's multipliers method? First take this c this side, then g minus c, let it be h, another function. Then the NLPP can be written as optimize z equal to f of x1 x2 subject to constraint, only one constraint, h of x1 x2 equals 0, then x1 x2 greater than or equals 0. Then construct the Lagrange's function. How to construct Lagrange's function? Always remember objective function. This is objective function minus lambda into constraint. Lambda into constraint. What is this lambda? Is called Lagrange's multiplier. And for the optimization, that means to find maxima and minima, the necessary conditions are what? First order partial derivatives of L with respect to unknowns x1, x2, and lambda equal to 0. So I got three equations. Solve them for three unknowns. What are the three unknowns? x1, x2, and lambda. After getting this point, now we have to check whether this point gives maximum or minimum. For that, you directly go to this one, Hessian matrix. What is Hessian matrix of the function f of x1, x2? Find all the second order partial derivatives of f. 1 1 position. Remember how to remember this. 1 1 position means x1 into x1 squares, first partial derivative. This is 1 2 position. 1 2 position means f derivative with respect to 1 and 2, x1 and x2. This is 2 1 position. That is f partial derivative with respect to x2 and x1. This is 2 2 position, means f second derivative with respect to x2. Then how to decide maxima and minima? It gives the positive definite or negative definite of h of x. H of x is called positive definite. Then f of x, the function has a minimum value, and the function is called convex function, and it has minimum value. And when I say the h of x is positive definite, you find out, you take the first element, this element, dou square f by dou x1 square, find its determinant positive. You take the 2 by 2 determinant, it is positive. If all the principal minors are positive, then h of x is called positive definite. Then the function is having minimum value. Now another one, negative definite. When the function is negative definite, h of x is negative definite, function is called concave function. Then it has maximum value, the shape of convex function and a concave function like this. And when it is called negative definite, if the principal minors are alternately negative and positive, alternately negative and positive. Now this is case 1 with what? Only one equality constraint. Now case 2, more than one equality constraints. More than one equality constraints. If you have any doubts, you can raise the questions. Okay, more than one equality constraints. Now consider the NLPP optimize z equal to, let me consider n variables. So let me, I am generalizing this now, subject to constraints. How many constraints shall I take? Gi, I will write x1, x2, xn, x1, x2, xn, equality constraints. Remember, I, and I is from where to where? I is from 1 to m. 1 to m means what? M constraints are here. G1, G2, Gm, m constraints are there, and all the variables, how many variables? N variables are there. Xj greater than or equal to 0. Any doubts in this one? I'm generalizing this. First case is one with one equality constraints. We have the concept of maxima and minima, Lagrange's multipliers. Now m constraints, more than one equality constraint, m constraints. Same logic. Let hi of x1, x2, xn equal to, what is assumption? Take that c onto the left side, minus ci, minus ci. Then NLPP can be written as, optimize z equal to f of x1, x2, xn, subject to, what is this constraint becomes now? Hi of x1, x2, xn equal to what? 0. This is for I equal to 1 to m. M constraints are there, and all the variables greater than or equal to 0. 1 to n. J is 1 to n. Now, after this, what we did previously? Lagrange's function. Now, construct the Lagrange's function. Lagrange's function as, now L stands for Lagrange's function. How many variables we have? X1, x2, xn. How many constraints we have? M constraints are here. So there will be m Lagrange's multipliers equal to, what I told you, first write the objective function minus lambda 1 into first constraint, minus lambda 2 into second constraint, dash, what is the last one? Mth constraint, lambda m into mth constraint. This is the Lagrange's function. So I will write this Lagrange's function in a short way. L of capital X lambda, capital lambda equal to function x1, x2, and so on, xn, minus, I will club this one into summation, I equal to 1 to m. What is this? Lambda I can write and this is hi x1 x2 xn, x1 x2 xn. This is the Lagrange's function. Here what is capital X stands for? N variables. Capital X stands for n variables, and lambda stands for m Lagrange's multipliers. M Lagrange's multipliers. Here lambda 1, lambda 2, lambda m are Lagrange's multipliers. Lagrange's multipliers. Any doubts? This is construction of Lagrange's function with m equality constraints. With m equality constraints. Now total number of unknowns. How many unknowns are there? How many unknowns are there? x1 x2. How many unknowns? x1 x2 xn. And how many Lagrange's multipliers? 1 2 m. Okay, therefore the necessary conditions for optimum, for maximum or minimum, for optimum are, all of you, previously what we did, two variables, dou L by dou x1 equal 0, dou L by dou x2 equal to 0. Now all the variables, how many variables? Dou L by dou xj equal to 0, j equal to 1 to n variables are there. And what are the another unknowns? Another unknowns are what? Dou L by dou lambda I. Lagrange's multipliers are also there. Therefore 1 to m. 1 to m. These are the necessary conditions. These are the necessary conditions. Totally, here we have how many equations totally? Here we have how many equations? N equations here, m equations here. We have n plus m equations with how many unknowns? With n plus m unknowns. With m plus n unknowns. What are the unknowns? I will write here x1, x2, and so on, xn, lambda 1, lambda 2, and so on, lambda m. These are the unknowns. Okay, so n plus m equations, n plus m unknowns, I can solve. Okay, solve the above equations. Solve the above equations for the stationary point. For the stationary points. What are the stationary points? You may get one solution or more than one solution, and values of lambda. Values of lambda. Now I have to decide whether the stationary point gives maximum or minimum. Stationary point gives maximum or minimum. Now to decide whether the stationary point, x equal to x1, x2, and so on, xn gives maxima or minima to f of x1, x2, xn, we have to evaluate the following determinants in the matrix. Following determinants in the matrix given by. Now this is important. You have to remember this. In the matrix given by, now delta n plus 1 equal to, all of you listen carefully, 0, 0. Okay, next one, if it is a single constraint, all of you, one more thing, single constraint we have, I will write like this. Don't confuse, listen carefully. Given by, here point A I am giving, point A, for optimize z equal to f of x1, x2, and so on, xn, subject to h of x1, x2, and so on, xn equal to 0, xj greater than or equal 0. What is this? Objective function with n variables, only one constraint. I'm taking here one constraint, like previous case one is what? One constraint with two variables. Now here how many variables? N variables. For remember this, for this one, delta n plus 1 equal to delta n plus 1 equal to, you remember this, all of you, this is the condition for this one constraint, n variables with one constraint. First you write 0. First you write 0. Then this first constraint, only one constraint is there now. Write its first order partial derivatives with respect to the variables, with respect to the n variables in the first row. Same expressions in the first column, dou h by dou x1, dou h by dou x2, and so on, dou h by dou xn. This is the first row and first column. All of you, I'm underlining this because this is one way. Now you write the Hessian matrix of L. Hessian matrix always, what is meant by Hessian matrix? Remember, always Hessian matrix means second order partial derivatives matrix. Second order partial derivatives matrix. Now, from this point onwards, this point, these positions are there now. You consider these positions as a new matrix. Now, taking this one as 1 position, for L, you write its derivative with respect to x1. 1 position means double derivative with respect to x1. This is 1 position. 1 position means what? With respect to x1, x2, and so on. This is what position? 1n position. Dou x1, dou xn. Okay, now coming to this position. Okay, this is by treating this position as 2-1. Okay, 2-1. That means x2, x1. This is 2-2. Dou square L by dou x2 square. This is 2n position. So x2 and xn. And lastly, what is this? Is nth row. So dou L by this is nth row xn x1 position. Dou square L by dou xn x2 position, and so on, dou square L by dou n position xn square. And what is this order of the matrix? N plus 1 order, 0 to n. How many values? 0 to, this 0 to n means n plus 1. Here also this is n plus 1 by n plus 1 matrix. N plus 1 by n plus 1 matrix. Now, in this matrix, if delta 3, all of you, delta 3 means, let me write, okay, at side I will write delta 3, that means third order principal minor. Delta 3 greater than 0, delta 4 less than 0, delta 5 greater than 0, that is the signs. That is the signs pattern. The signs pattern being alternate. The signs pattern positive, negative being alternate, then the stationary point is a local maximum. Local maximum. This is the first point. Next one. If delta 3 negative, delta 4 negative, delta 5 negative, the sign pattern, the sign being always negative, the stationary point is a local minimum. Okay, what is meant by local minimum, local maximum? See, if I consider one curve like this, right? This is minima, right? Okay, if I just consider curve like this, okay, this is also another minima. These are all local minimas. In this all local, this is local minima. Same logic, local minima. and this is there now, this is global minima. This is global minima. Same logic, maxima. This is one maximum, another maximum, another maximum. These are all local maximum, and this is called global maximum. This is called global maximum, and these are called local maximum. Local maximum, like this. So what is a single constraint with n variables? If the determinants of delta 3, delta 4, delta 5 gives alternate sign pattern, positive, negative, positive, negative, then the stationary point gives local maximum. If the all the principal minus delta 3, delta 4, delta 5 are negative, and so on, then it stationary point gives local minimum. Okay, and now coming to, I will explain this delta 3 like this. Delta 3 means what? Delta 3 means what? This is first determinant, just I'm showing here. This is the first part, delta 3. Next, delta 4 means you extend one row and one column, delta 4, like that. Okay, that is meaning of delta 3 and delta 4, and delta 5 also. Okay, now do h, right. This is with what is this case? For the what problem? A objective function with n variables with a single constraint. Now if I multiple constraints are there, I will take like this. For optimize z equal to f of x1, x2, xn subject to hi, subject to hi of x1, x2, xn equal to 0, I equal to 1 to m, I equal to 1 to m, xj greater than or equal to 0. Now this is the problem. That means with what? N variable function and m constraints are there. N variable constraint and m constraints are there. Here, let capital V, I'm taking, what is capital V? Dou square L by dou xi dou xj. This is the matrix. This is the matrix, n by n matrix. This is the n by n matrix. And capital U. Capital U is what? Dou hi by dou xj. This is another matrix. Dou hi by dou xj. What is the matrix order? M constraints are there, n variables are there. For your clarification, I'm giving this. Dou square L by dou x1 square, dou square L by dou x1 x2, like this. Dou square L by dou x1 xn, dou square L by dou x2 x1, dou square L by dou x2 square, dou square L by dou x2 xn, and so on. Lastly, nth row, dou xn x1, dou square L by dou xn x2. You have to listen compulsory, because we have to solve the problems. So method is very important. This is about this. And what is this one? This is dou h1 by dou x1, dou h1 by dou x2, and so on, dou h1 by dou xn. Same. Another one is what? Second constraint, dou h2 by dou x1, dou h2 by dou x2, and so on, dou h2 by dou xn. Okay, and this is da da dash dou h m, mth constraint, dou x1, dou h m by dou x2, and so on, dou h m by dou xn. So m rows are there and n columns are there. This is n by n matrix. Okay, see, in multiple constraints, equality constraint, m constraint, this is the technique. Find v. V stands for what? Lagrange's function second order derivatives. And u stands for what? For constraints first order partial derivatives. Then define a square matrix. Now define a square matrix. This square matrix is represented by HB. HB. And what is this? Yeah, power is went off. Okay, internet problem. Just now I connected through a hotspot. Now screen is visible.
No, sir.
Yes.
No, sir. No, sir.
Not visible. Now okay.
Yes,
Now
sir.
screen is okay.
Yes, sir.
Yes, sir.
Okay, right. Now we have to construct a bordered Hessian matrix, okay, where the splitting is like this. Where the splitting is like this. 0 stands for, the 0 is M by M matrix. 0 is M by M matrix. Null matrix. 0 matrix here. And U stands for what? Already told you, U stands for first order partial derivative matrix of constraints. V stands for second order partial derivatives of Lagrange's function. Second order partial derivatives of Lagrange's function. Now this is the most important content you have to remember. Then here the stationary point x star and lambda star, that means values of x1 x2 xn and lambda 1 lambda 2 lambda n. Okay, the stationary point, this here first point, maximum value gives maximum value if starting with this is important, all of you catch this point, starting with principal minor of order 2m plus 1, starting with principal minor of order 2m plus 1 comma the last n minus m principal minors, last n minus m principal minors of hb star means evaluated at this point, minors of hb form an alternating sign pattern, an alternating sign pattern starting with minus 1 whole to the power of m plus n, minus 1 whole to the power of m plus n. And second point gives minimum value, the stationary point gives minimum value if starting with principal minor of order 2m plus 1 comma the last n minus m principal minus of hb have the sign of minus 1 whole power m, have the sign of minus 1 whole power m. If I explain this, I will explain these 2 points in the problem, okay. Now this is the concept of Lagrange's multipliers method with the equality constraint, one equality constraint, and more than one equality constraint, Now see the problem. Solve. I will tell with the one equality constraint and more than one equality constraint. Solve the NLPP. minimize z equal to 2x1 square minus 24x1 plus 2x2 square minus 8x2 plus 2x3 square minus 12x3 plus 200, subject to constraint x1 plus x2 plus x3 equal to 11, and the non-negative restrictions are x1 x2 x3 greater than or equal to 0, x1 x2 x3 greater than or equal to 0. Now solution. Here, what is the function? How many variables are there? 3 variables are there. So f of x1 x2 x3, the objective function is what? 2x1 square 24x1 plus 2x2 square minus 8x2 plus 2x3 square minus 12x3 plus 200. And what is the constraint? I will take directly h of x1 x2 x3. What is this constraint? Left side minus right side, x1 x2 x3 minus 11. Got it? Now define the Lagrange's function. Define the Lagrange's function. L. How many variables? x1 x2 x3. How many constraint? Only one constraint, then one Lagrange's multiplier equal to, what is this? Once again I will write the first formula, minus lambda into h x1 x2 x3, minus lambda into h x1 x2 x3. So let me substitute x1 x2 x3 lambda. This is 2x1 square minus 24x1 plus 2x2 square minus 8x2 plus 2x3 square minus 12x3 plus 200 minus lambda into x1 plus x2 plus x3 minus 11. Minus 11. Now Lagrange's function is over. Now what are the necessary conditions? I told you the necessary conditions for optimum. What is the given problem? Minimum, na? The necessary conditions for minimum or maximum are dou L by dou x1 with respect to unknowns, partial derivatives of L with respect to unknowns equal to 0, x3 equal to 0, and what is the last one? Dou L by dou lambda equal to 0. Lambda is called Lagrange's multiplier. Lambda is Lagrange multiplier. Lagrange multiplier. Now one by one let me solve. Dou L by dou x1 equal to 0. What this gives? 4x1 minus 24. That's it. In terms of lambda, minus lambda. x1 derivative 1. So minus lambda will be there. Next, dou L by dou x2 equal to 0. This is what? 4x2 minus 8. This is also minus lambda equal to 0. Right? Next, dou L by dou x3 equal to 0. This is what? 4x3 is there. 2x3 square derivative. Minus 12 will be there, and minus lambda equal to 0. And lastly, dou L by dou lambda equal to 0. So lambda derivative minus 1 into this part as it is, x1 plus x2 plus x3 minus 11 equal to 0. Minus 11 equal to 0. Now I have to solve this problem for x1 and x2. What I will take here, what is x1 is nothing but lambda plus 24 by 4. From this, what is x2 is nothing but lambda plus 8 by 4. From this, what is x3 is nothing but lambda plus 12 by 4. Okay, and this is what? Just x1 plus x2 plus x3 minus 11 equals 0. So 11. Okay, take this as 1, 2, 3, and this is 4. Substitute 1, 2, 3 in 4. So 4 implies what? x1 plus x2 plus x3 equal to 11 implies lambda plus 24. Anyway, 4 is the LCM. Okay, lambda plus 8, lambda plus 12 whole by 4 equal to 11. So this implies what? 3 lambda and 24 plus 8, 32, 42, 44. 44 equal to, this is also 44. So what is lambda? Is nothing but 0. Lambda is nothing but 0. Therefore, what is x1? X1 is lambda plus 24 by 2. Therefore, 1 implies, I will write. Therefore, 1 implies lambda value 0. Lambda value 0 means 24 by 4, 6. 2 implies x2 equal to lambda plus 8. So 8 by 4, that is 2. And the equation 3 implies lambda plus 12. Lambda 0, so 12 by 4, 3. Therefore, stationary point is capital X equal to, or X star you take. What is that? 6 comma 2 comma 3 with the lambda equal to 0. With lambda equal to 0. Now, see, what is this problem, all of you? Now, let me go to the method also. Only one equality constraint with the 3 variables, not 2. What are 3 variables? Therefore, just wait. Why it is not moving? Yeah. Now, with one constraint, I have to, yeah, exactly. With one constraint, more than 2 variable, what I have to construct? This way, this one, delta n plus 1, I have to construct. 0, constraint derivative with respect to the variables, first row and first column same. Next one, from here onwards, this part, from here onwards, for Lagrange's method, the second derivatives. For Lagrange's method, second derivatives. Therefore, now you write like this. Now, yeah, to decide, to check whether x star gives minimum to the objective function, okay. For this, construct what is delta n plus 3, means delta n plus 1, n value 3 here, so this becomes 4. What is this matrix? 0. Already told you, first row h derivatives with respect to variables. How many variables are here? Only 3 variables are here. Same, first column also same. Dou h by dou x2, dou h by dou x3. This is over. Now, from here onwards, what are these positions? Second order partial derivatives of L. This is dou square L by dou x1 square, dou square L by dou x1 x2, dou square L by dou x1 x3. Next, this is dou square L by dou x2 x1, dou square L by dou x2 square, dou square L by dou x2 x3. Next, this position, dou square L by x3 x1, dou square L by x3 x2, dou square L by dou x3 square. How to remember this? I told you how to remember this. This part is there now. This part is second order partial derivatives of L, and treat this as again new matrix, 1 1 position, 1 2 position, 1 3 position, like that. Okay. Now let me substitute one by one. This is delta 4 equal to 0. What is h? I'm writing here. What is h? X1 plus x2 plus x3 minus 11. So what is the derivative with respect to x1, x2, x3? 1. Now I have to see what is L. That is important now. What is L? Yeah, this is L. For this L, I have to consider derivatives, second derivatives. So dou square L by dou x1 square. First one is 4. One more derivative with respect to x1, you will get 4. Okay, let me write. You can check that clearly, right? So dou square L by dou x1 square 4. Dou square L by dou x1 x2 0, x1 x3 0. You will get these values. You can find the derivatives. You know how to calculate partial derivatives. Now this is 4 by 4 matrix. What I have to consider now? Delta 3. See the conditions. Already I told you the conditions. Find delta 3, next delta 4, like that. Delta 3 means what? I told you delta 3 means what? This first 3 by 3. So I'm writing that 0, 1, 1, 1, 4, 0, 1, 0, 4. What is its determinant? The first value 0 minus 1 into this is 4 minus 0 plus 1 into this one 1 minus 0. So minus 4, is it correct? Minus 4, 0. First one is 0, doesn't matter, right? Next second one minus 1. This one gone, 4 minus 0, correct? Next this is 1, 1 gone, yeah. No. This is 0 minus 4, 0 minus 4. So minus 4 minus 4 minus 8 negative. Delta 3 is negative. Done? Now coming to delta 4. Delta 4 means entire matrix. What is this matrix? 1, 1, 1. 4 0 0 0 4 0 0 0 4 0 0 4. Okay, now I have to calculate this and determinant. For this, what, let me simplify, otherwise it is very big one. What is the simplification? R3 minus R2, R4 minus R2 I will take. So there is no change in the first row, no change in the second row. Change belongs to what rows? Third row and fourth row. So 1 minus 1, 0. 1 minus 1, 0. R3 minus R2. This becomes minus 4. This is 4. This is 0. 1 minus 1, 0. Minus 4, 0, 4. Now, expand the determinant using the first column. First column expansion is by using first column 0. First one 0 into something 0. Minus 1 into what? Minus... minus 1 into what? 1 into what is the determinant? This one gone, right? So 1 1 1 minus 4 4 0 minus 4 0 4, and remaining are zeros now. 0 plus 0 minus 0. That's it. This is the one way of simplifying the determinant. So this is minus 1 into 16 minus 0 minus 1 into this one gone, minus 16 0 plus 1 into this one, this is 0 plus 16. So what is this value? This value is minus, this is 16, this is plus 16 plus 16. So minus 48. This is also, delta 4 is also negative, right? As I told you, what is the condition? Previously we have seen, what is this? In the method, alternate sign pattern, it gives maximum value. All are negative, it gives minimum value, right? I will show you that. Yeah, not this. Yeah, see, all are negative, it gives minimum value. Alternate sign pattern, maximum value. Now here, delta 3, delta 4 negative, delta 3, delta 4 negative, right? Since delta 3 less than 0, delta 4 less than 0 at the stationary point. At the stationary point, I have to evaluate this determinant at the stationary point. What is the stationary point? 6 2 3. This point gives minimum to the objective function. Minimum to the objective function. Therefore, minimize f of x1, x2, x3 equal to, what is the function actually? Function is what? 2x1 square, 2 into 6 square, minus 24 into 6, plus 2 into 2 square, minus 8 into 2, plus 2 into 3 square, minus 12 into 3, plus 200. You find this value, that is the answer. You find this value, that's the answer. Any doubts? Any doubts? Yes, this is the problem with one single constraint. one single equality constraint. Any doubts? Yes. Next problem. Solve the NLPP. Optimize z equal to 4x1 square plus 2x2 square plus x3 square minus 4x1 x2, subject to the constraints x1 plus x2 plus x3, x1 plus x2 plus x3 15, 2x1 minus x2 plus 2x3 equal to 20, and x1 x2 x3 greater than or equal to 0. Now how many equality constraints? Two equality constraints are there. So our second case, try to solve this. Just give me 2 minutes. Yes, anyone? Is first problem is clear? Say yes or no. Yes, students, are you there?
Yes, sir.
Yes, sir.
Yes, sir.
Tell, just reply. Is first problem is clear?
Yes, sir.
Okay. Now, coming to what is this problem structure? Three variables objective function with two equality constraints. Two equality constraints. So, I'm starting. The objective function is what? F of x1, x2, x3 equal to 4x1 square plus 2x2 square plus x3 square minus 4x1, x2 minus 4x1, x2. And what the constraints I have to assume? First constraint, h1 I am taking. What is that? Left side minus right side. So minus 15. Second constraint is what? F of x1, x2, x3 equal to 2x1 minus x2 plus 2x3 minus 20. Minus 20. Now declaration of the functions and constraints is over. Now construct the Lagrange's function. Construct the Lagrange's function. Okay. Construct the Lagrange's function as L. How many variables? X1, x2, x3. And how many constraints? 2 constraints are there. Therefore, 2 Lagrange's multipliers. So I will write function of x1, x2, x3 minus lambda 1 into first constraint minus lambda 2 into second constraint. Now let me substitute. L I will write directly 4x1 square plus 2x2 square plus x3 square minus 4x1 x2 minus 4x1 x2 minus lambda 1 into x1 plus x2 plus x3 minus 15 minus lambda 2 into 2x1 minus x2 plus 2x3 minus 20 minus 20. Now this is the Lagrange's function. Now the necessary conditions. The necessary conditions for optimum. Optimum means maximum or minimum. Optimum are dou L by dou x1 with respect partial derivatives of L with respect to unknowns equal to 0. So unknowns are x1, x2, x3 and lambda 1, lambda 2 all also unknowns. So totally 5. Totally 5. Now 1 by 1. Dou L by dou x1 equal to 0. So what is this is 8x1 minus 4x2 minus lambda 1 minus 2 lambda 2 equal to 0, right? X1 derivative 1, here 2, so this one. Next, dou L by dou x2 equal to 0. This is 4x2 minus 4x1 minus lambda 1 plus lambda 2, this is plus lambda 2 equal to 0, right? Next one, dou L by dou x3 equal to 0. Dou L by dou x3 means what? What is the function? Yeah, 2x3 minus lambda 1 minus lambda 1 minus 2 lambda, what is this? What is this? 2 lambda 2 minus 2 lambda 2 equal to 0. This is the third one. Okay. Next one, dou L by dou lambda 1 equal to 0 means what? X1 plus x2 plus x3 minus 15 equal to 0 with minus sign. Dou L by dou lambda 2 equal to 0 is what? Minus 2x1 minus x2 plus 2x3 minus 20 equal to 0. Done. Now one by one I will write here. So what I am getting here, from this expression, this is x1 plus x2 plus x3 equal to 15. From this expression, 2x1 minus x2 plus 2x3 equal to 20. From this expression, what is x3 equal to? Lambda 1 plus 2 lambda 2 by 2 by 2. And from this, take this as 1, take this as 2, take this as 3, this as 4, and this as 5. I have to solve this. See, 1 plus 2, what this gives? 1 plus 2, 1 plus 2 means this plus 4x2 minus 4x2 gets cancelled, right? So 1 plus 2, 8x1 minus 4x1 is 4x1. These two, 1 plus 2 minus 2 lambda 1 will be there, and plus means minus lambda 2 is there. So what is x1 value? 2 lambda 1 plus lambda 2. Done. By 4, x1 is okay. This is equation 6. Now I have to get x2. Okay, what is 4x1 from this? 2 lambda 1 plus lambda 2. Then substitute 4x1 value in 2. 2 implies, yeah, 2 implies 4x2. 4x2 minus 4x1 na? Minus 2 lambda 1 plus minus lambda 2 minus lambda 1 plus lambda 2 equal to 0. Is it correct? Minus 4x1 minus 2 lambda 2, right, done. Next one. So from this, what is x2 equal to? This is 3 lambda 1 by 4. 3 lambda 1 by 4. Okay, now I got x1, x2, x3. Put x1, x2, x3 in 4 and 5. In 4 and 5. This x2 value, next one this x1 value, and next one this x3 value. In what equations? These two expressions, x1 plus x2 plus x3 equal to 15. First expression, okay. Oh, yeah. 4 and 5. 4 implies x1 plus x2 plus x3 equal to how much? 15. Implies, what is x1 value? What I got x1 value? 2 lambda 1 plus lambda 2 by 4. x2 value 3 lambda 1 by 4. What is x3 value? Lambda 1 plus 2 lambda 2 by 2. X3 value, yeah, by 2, correct, equal to how much? 15. So what I'm getting here, 2 lambda 1 plus lambda 2 plus 3 lambda 1 plus 2 lambda 1 plus 4 lambda 2 equal to 60. 15 LCM. So 2, 3, 4, 7 lambda 1 plus 5 lambda 2 equal to 60. This is equation number 8. Next value. What is equation 5 implies? 2x1 minus x2 plus 2x3 equal to 20 implies 2x1. I will write as it is. 2x1 means what? 4 lambda 1 plus 2 lambda 2 by 4. I am keeping 4 as it is. Minus 3 lambda 1 by 4. And coming to this, 2 lambda 1 plus 4 lambda 2 by 2 equal to 20. Now take 4 LCM. 4 lambda 1, 2 lambda 2 minus 3 lambda 1, 4 lambda 1 plus 8 lambda 2 equal to 80. Equal to 80. So what is this? Lambda 1, 5 lambda 1 plus 10 lambda 2 equal to 80. So lambda 1 plus 2 lambda 2 equal to 60 now. Right? This is 9. This is 9. Now solving 8 and 9. Solving 8 and 9. Okay, we get, you know how to solve. 7 lambda 1 plus 5 lambda 2 equal to 60. Multiply this by 7. 7 lambda 1 plus 14 lambda 2 equal to 42. 112. Subtract. These two gets cancelled. 14 minus 9. Minus 9 lambda 2 equal to how much? 112 minus 60. 2. 11, 5, 52. 52. So we get lambda 1 equal to lambda 2 equal to how much? 52 by 9. Lambda 2 equal to minus gets cancelled, 52 by 9. And lambda 1 you will get 40 by 9. 40 by 9. Then x1 equal to, you substitute in x1, x2, x1. You know the expressions now? In this one, put lambda 1 value. Next one, in this one, put lambda 1, lambda 2 values. Okay, then you will get x1, x2, x3. X1 equal to, you will get 33. X1 equal to 33 by 9. X2 equal to 10 by 3. And x3 equal to 8. Therefore, stationary point is x star. I am taking x star equal to 33 by 9, 10 by 3, 8. Now to check whether oh wait, now to check whether x star gives max or min, we have to find the bordered Hessian matrix. What is that? I told you bordered Hessian matrix. HB I told you. Do you remember? HB. What is that matrix? In the method 0, U will be there, U transpose will be there, and V. V. Okay. And what is here? UO is M by M null matrix. M by M null matrix. Next, what is U? Dou Hi by dou Xj. This is what? M by N matrix. And what is V matrix? Dou square L by dou Xi Xj. N by N matrix. So first we have to find all these. So one by one I am calculating. Now first one, 0 already it is over. M means here, M equal to how many constraints? 2, N equal to variables 3. M stands for number of constraints, N stands for number of variables. So U, dou Hi by dou Xj, M by N means nothing but what is this matrix? 2 by 3 matrix equal to first constraint dou H1 by dou X1, dou H1 by dou X2, dou H1 by dou X3. First constraint is over. Second constraint derivatives, dou H2 by dou X2, dou H2 by dou X3. So what is this? U H1 is what? X1 plus X2 plus X3. So derivatives are 1. And H2 is was 2x1, that is 2, minus X2 and 2x3. H is over. U is over now. U is over. Now coming to V. What is V? Dou square L by dou Xi, dou Xj. Nothing but N by N matrix. N by N means what? 3 by 3 matrix. Okay, 3 by 3. So dou square L by 1 1 position, X1 square, 1 2 position, X1 X2, 1 3 position, X1 X3. Next, second row, 2 1 position. This is next. This is 2 2 position. So X2 square. This is 2 3 position. 2 3 position. 2 3. Next one. Dou square L by 3 1 position. 3 1. 3 2. 3 2 and 3 3. Okay, for L I have to consider. So if I find this, you will get 8 minus 4 0 minus 4 4 0 0 0 2. This is the matrix. So hence now I can write HB, bordered Hessian matrix. Therefore HB equal to, what is the first one? 0 matrix, M by M. M by M means 2 by 2 matrix. So let me split. Okay. Now what is this? Hey, U matrix, 1 1 1, 2 minus 1 2. So I have to write this one. Transpose, U transpose, 1 1 1, 2 minus 1 2, 2 minus 1 2 over. Now here what I have to write? V matrix. V means what? This one. 8 minus 4 0 minus 4 4 0 0 0 2. Now this is the bordered Hessian matrix. What is the order? 5 rows are there and 5 columns are there. Now, whatever the thing I told now, the 2 points. Okay, now let us evaluate that. HB star I will write. Star stands for what? At the stationary point also. Since it is a constant matrix, doesn't matter. Now, what are those two conditions, those two criteria? Yeah. What is the first criteria? Starting with the principal minor. Starting with the, understand this point, principal minor of order 2m plus 1. M stands for 2. 2 into 2. M stands for constraints. So I have to start with what order determinant? Fifth order, means 5 by 5 determinant. Starting with the principal minor of order 5. The last n minus m, that is 3 minus 2, 1. Principal minors of HB star, okay, form, if I say, form an alternating sign pattern, starting with minus 1 whole power m plus n, then x star gives minus 1 whole power m plus n means what? Minus 1 whole power 3 plus 2, that is negative minus 1, negative sign. Then x star gives maximum point. Or if starting with principal minor of order 2m plus 1, that is fifth order, the last n minus m, that is 3 minus 2, 1. Principal minors of HB star have the sign of minus 1 whole power m. Minus 1 m means number of constraints, positive, that is positive. Then x star gives minimum point. Now the main understanding is here what? I have 5 by 5 determinant HB. So starting with what? Fifth order determinant. That means I have to calculate first 5 by 5, and there is no question, last n minus 1. That means after 5 by 5 determinant, you have to calculate one more. That means 6 by 6. Is there any 6 by 6 matrix here? No, only 5 by 5 matrix is here. Since that we have to mention, that means we have to find only 5 by 5 matrix determinant. If it has the sign negative, then it gives what is the point? Maximum point. And if it has the sign of minus 1 whole square, positive, then it gives minimum. Clearly, we have to find 5 by 5 determinant. We have to find 5 by 5 determinant. Clearly, we have to find 5 by 5 determinant. And one more is not there. 5 by 4 determinant only. Since no matrix of order 6 by 6. Last 1 minus 1. That is the meaning of this. Take one more determinant. Okay, 5 by 5 determinant only. So determinant of HB star. Oh, we have to find this determinant. This is 0, 0, 0, 0, 1, 1, 1, 2, minus 1, 2. Oh, shit. Yeah, let me cancel this. It's not moving properly. Okay. Now what is the determinant? 0, 0, 0, 0, 1, 1, 1, 2, minus 1, 2, 1, 1, 1 transpose now. 2, minus 1, 2. Next 8, minus 4, 0, minus 4, 4, 0, 0, 0, 2. 0, 0, 2. Same logic. What is the application? You first row, second row, third row, fourth row, fifth row. Let us make these two positions to 0 using this 1. That means R4 minus R3, R5 minus R3. If I do like this, it is better with 1 only. Third row, using first column, I can expand this determinant. So up to third row, there is no change. But 1 minus 1, 0, minus 1, minus 2, minus 12, 8, 0. Coming to this is 0, 2 minus 2, 0, 0 minus 8, 0 minus of minus 4, this is 2. Right? Now, I have to evaluate with 1. With 1 means what? With 1, okay, with 1, this one. And what is the plus minus sign? Plus, plus, minus, plus. So this is 1 into remaining 4 by 4, remaining matrix determinant 0, 1, 1, 1, 0, 2, minus 1, 2, minus 3, minus 12, 8, 0, 0, minus 8, 4, 2. Next one, this is you evaluate using this 3. Evaluate using this 3. Okay, what is this value? 4. Now evaluate using this 3 again, right? What finally you will get the value as 90. Value as 90. 90 means what? This HB. So determinant of HB star is what? 90 positive. Have the sign of, what is the sign? As the sign of minus 1 whole power m, that is minus 1 whole square. Hence x star, what is that point? X star 33 by 9, 10 by 3, 8 gives what value? Gives minimum value. Gives minimum value to the objective function. Minimum value to the objective function. Now you substitute this one. Therefore, minimum of f of x1, x2, x3. You substitute this value, x1 value, x2 value, x3 value in the function. That is 4 into 33 by 9 square plus 2 into 10 by 3 square plus 8 square minus 4 into 33 by 9 into 10 by 3. Okay, you find this value. Find this value. Any doubts in this problem? This is with two equality constraints. With the 2 equality constraints. And you take this problem as assignment. Try this. Solve. Minimize z equal to x1 square plus x2 square plus x3 square subject to constraints x1 plus x2 plus 3x3 equal to 2. 5x1 plus 2x2 plus x3 equal to 5. x1 x2 greater than or equal to 0. x1 x2 greater than or equal to 0. 2x2. Okay, try this. Okay, answer I'm giving 37 by 46, 16 by 46, the point, stationary point, finally 13 by 46, 13 by 46. Now, any doubts in this Lagrange's method? Any doubts? If no doubts, I will stop. I will stop here. Any doubts?
No doubt, sir.
Okay. Please, all of you solve that problem. Okay. If any doubts, it will be clear for you. Right. Thank you.
Thank you, sir.